Let us now give an interesting formulation of what we already have seen. So we have seen and proved the following corollary of the main theorem, which connected the Nash equilibria of zero-sum games, or constant sum in general even, with max-min. So the corollary is as follows. First, given any two Nash equilibria, we can shuffle which strategy of one player goes with which strategy of another player. So xy being in Nash equilibrium and also x prime y prime being in Nash equilibrium imply together that x with y prime or x prime with y also are Nash equilibrium. And the other thing, and that's the thing we are going to use to arrive at an interesting formulation, and the other thing is that a constant sum game has an equilibrium if and only if max min of u1 equals to min max of u1. And also, as we said after the corollary, that when that happens, that max min of u1 equals to min max of u1, we call this equal one to the other utility the value of the game. And now let us formulate something else which is similar. The new corollary is that the max min of u1 is all this, not even for zero sum. Actually, here it is for zero sum. But for any zero sum game, max min of u1 is at most c minus max min of u2. So the best that u1 can guarantee, despite whatever u2 does, or let's say when the u2 does, when the second player does the worst for the first player, is at most c minus, let's assume c is 0 for simplicity, is at most the minimum of what the second player can guarantee when the first player tries to destroy the situation of the second. So minimum, of course, results from the fact that the utilities, if I assume c is 0, that they are together, they sum up to 0. So the best I can guarantee, and I assume the other person is trying to hurt me as much as possible, is the minus of the best that the other person can guarantee, is at most, the minus that the other person can guarantee when I hurt it as much as possible. And intuitively, that's actually very, very, very reasonable because the best I can guarantee is minus the worst the other person, because we are bound to have a sum of 0. But the concrete proof is something that you will do at homework 2. But what we are going to see now is the proof of the second part, is that a constant sum game has an equilibrium if and only if the above equality is actually holds with the above inequality holds with equality. So when the best I can guarantee is exactly what is minus the best the other person can guarantee, it's a bit similar to this duality of LP. And by the way, we can use LP to prove such things, but we don't do it because it won't necessarily be very simple, and it won't necessarily be very insightful. So maybe actually it's a good idea to use LP. Historically, those things were done, I think, before LP, because those things were probably done by von Neumann and Morgenstern in the end of 27, while LP was formulated by Kantarovich in the 30s, and in the West, from what I remember, it was adapted in the West in the 40s even. So LP is a later technique. Anyway, let us prove the second thing. So please let's go to the previous slide. And then we said that a constant sum has an equilibrium if and only if max min of a player is the same as min max. And we also said that, or maybe we didn't say, but that's true, that max min is always at most min max. So one order of taking max and min is always at most as the other one. And equilibrium is equivalent to those results being equal. Those. And I can also reformulate this condition as this condition. That's what we are going to do now. So it's always, as I said, that max min is most min max. That's something that you're going to prove at the homework too. Now, lemma that we saw implies that the right hand side is actually equal to C minus max min of the other player. That the min max of U1 is C minus max min of U2. That is the lemma that we proved. And then the characterization that we saw, that constant sum has an equilibrium if and only if max min of U1 is equal to min max of U1, basically gives us the characterization that we want using this lemma. Okay, so we have found that this idea that max min is at most C minus, max min of one player is at most C minus max min of the other player. So the best I can guarantee to myself, and the other one tries to destroy my situation as much as possible, is the total sum minus the best the other person can guarantee to herself when I try to destroy her as much as possible. It's at most, because it can always be that we are both screwed in a way that nobody can guarantee anything good. So it's not like we match. For example, matching pennies is an example that we don't match, because I cannot guarantee better than 0, and so can't the other one. Wait a second, is yes, matching pennies is an example with someone. But these guarantees do match when there is an that's even only if there is an equilibrium. Okay, so another thing that we see is that a guaranteed payoff is exactly the best possible what we can get in an equilibrium when the equilibrium exists. So the guaranteed payoff of 1, for example, the symmetric, of course, is exactly the best possible one can get, which is the sum minus what the other can get, all this. So there is not only the motivation to act according to max min, because that is the best you can get, assuming the other one tries to hurt you, which is reasonable because you have a constant sum game. But there is also a reason which we can conclude from this corollary, that your max min is also the best you can get at all in an equilibrium. It's not only the best you can get and the other player tries to hurt you, it's also the best you can get in equilibrium. Okay, and let's recapitulate what we have seen in the wall in the lectures till now about zero sum, or constant sum in general. As I said, it's the same as zero sum. It's more general formula, but the logic is the same, simply it adds a bit more complexity that we need to drag this constant, and maybe it would be nicer not to drag it. Usually these games studied without this constant. So if you you want, you can remove the constant and then understand it better. So constant sum game, we find it, we've characterized the equilibria as that max min is equal to min max. That is the main theorem. So if it's an equilibrium, then both are max minimizers, and there is certain equality. Max min is equal to min max, and the other way holds as well. We conclude that the same utility is in all equilibria, and the equilibria are exchangeable. So if a strategy is an equilibrium strategy for a given player, it can be then paired with any equilibrium strategy for the other player, and they will have an equilibrium. So it's a very nice class of games, zero-sum games. Unlike the potential games, they don't always have an equilibrium, but the characterization when they do and all that is very nice. Okay, you're welcome to send me any questions, and goodbye.